So once again, good morning and welcome to today's class. I hope others will join as soon as possible. So we are going to discuss, let me share my screen. So we are going to discuss penalized regression. Before that, last week we discussed about subset regression. So are there matters arising from that lecture? I know I've given some practical questions, quiz. The quiz I gave, only 5 turned in their answers. So I've already closed the quiz, so nobody can submit again now. But we will review the solutions together before we finish, before the end of the class. So, if there are no matters arising, then we can just go on. So, penalized regression. The purpose of giving you the quiz in advance, or the pre-lecture quiz, is to compel you to go through the note to be able to answer. And I noticed that those who submitted they actually scored above, far above 10 out of 20, which is good, and it's also an indication that they have probably gone through the lecture notes in advance, so that our discussion now can be smooth and interactive if there are questions in between. So we know about regression, linear regression, and so on. And what we know about linear regression is the fact that in estimating the parameters of the model, we use the criterion which minimizes the sum of squares of the residuals. So we look for the coefficients that will produce residuals that will minimize the sum of squares of the residuals. So there is no penalty. There is no penalty, and therefore, once you run the regression, whatever estimate you obtain is considered to be the best linear, unbiased estimator. So that principle is extended. The principle of minimizing the sum of squares of the residual is extended to now involve penalizing the regression coefficients so that coefficients that are not really important can be shrunk either very close to zero so that their impact is minimized completely, or they are eliminated outrightly. So that's the role of penalized regression. So how do we do that? But even then, so there are three techniques that we'll be discussing. So one is the ridge regression. The second is the LASSO, which stands for least absolute shrinkage and selection operator. And the third is the elastic net penalized regression. So these three will be the focus of our discussion. We'll be interested in the criterion for each of them, and then of course how you can really choose the best, how you will choose, and we will also discuss the application areas, and then conclude with the software implementation. So at the end of the lecture, I expect you to understand the concept of overfitting in regression models, and also how penalized regression addresses this problem. You recall that I mentioned with penalized regression, coefficients can be shrinked or eliminated completely. So it allows you to do away with redundant variables in your model. This technique is widely used when you have high dimensional data sets. So we'll still talk more about that. Let's start with the issue of overfitting. And I deliberately brought this diagram again. We are familiar with it, but it's always very important for you to appreciate discussion in data mining, particularly the techniques we are employing in data mining. So I've explained this graph severally. Here you have the axis for the error. The total error is usually the bias square plus the variance. The total error is the bias square plus the error. So this is bias square, this is it. And this is variance, this is it. So the sum of the bias square and the variance gives you the total error. And on this axis, you have the model complexity. Here, the model is very simple. So maybe simple in terms of the function you have used, simple in terms of the variables, the number of features or independent variables that you have used. So, but either as you had more variables, you are making the model to become complex, or as you possibly include more functions in your model, then you are making the model more complex. So towards this side, we talk the model becomes complex. But when the model is simple, usually the bias square is very high, and then the variance is very, very low. What that means is that the model will do well outside the data used to train it. So when you use the model for new data, it's going to do well. That's what this one means. No. And but there will be problem within. So the model, in terms of the bias square, will be very high. So, but as you complicate the model, the bias square will come down towards 0. So it will reduce the bias, but the model variance will be very, very high, which means the model will not be able to perform very well outside the data used to train it. And that's not the kind of model you want. That situation is what we call overfitting. The situation where the model is able to capture only the noise, but not the signal, is underfitting. So this diagram shows you that the total error, which is the blue one, is minimized at the point where the bias square and the variance intersect. And this is the point. And that is the point where you have the optimal solution. So therefore, this technique, penalized regression, one major goal of using it is to avoid overfitting. Avoid overfitting means to have a situation where, to avoid a situation where the model is unable to perform in new data, but is able to do well in the data used to train it. So you want a model that is able, or that is able to mimic the data used to train it, as well as carry that knowledge of the data to new data sets. So that's always the goal of any modeler. So you want the algorithm or the model to have learned the dynamics, the interactions, the interrelationships in the training data set, such that when you now apply the algorithm or the model to a new data set, that same experience is used and the model is able to do well and predict outside the data used to model. If you have any question, let me know. So this is the basic reason why penalized regression is very important. So here I try to define overfitting occurs when a model is too complex. That is when you are in this zone. Having too many parameters, you have as many parameters as number of variables in your model. No, so when you have too many parameters relative to the number of observations, then you have very complex model. So such models will capture noise. Every model has, will capture noise, but we want model that will capture noise and signal. So two things. Signals are important, but you can't also avoid noise. So the signal is the main thing, but this noise is random, is the one that ordinarily is not observable, but it's always there. So when you have overfitting, your model capture the noise along with the underlying data pattern, which is the signal, which diminishes their ability to generalize to a new data set. So they perform poorly in new data set because they capture noise more than signals. So these are the characteristics of overfitting. One, you have high accuracy in the training data set. You remember what we do, we split the data into training and test data set. So the model will have high accuracy in the training data set, but poor accuracy in the testing or new data set. Another main feature is that there will be excessive swings in predictions. So the predictions will not be stable. And this is because any minor fluctuations in the input data will not be captured, because noise is only going to emphasize more on noise and not signals coming from the data. So the third main characteristic is the complex decision boundaries when you now visualize the data, so to say. So these are three main characteristics. Noise is captured more than signals when there is an overfitting, and predictions are poor outside the data used to train the model. Now, what are the causes of overfitting? No. What are the causes of overfitting? We have to trace it to the model complexity. One, too many predictors. When you have too many explanatory variables, that can lead to overfitting. Let me be sure. Is the class? Yes. I can see Mbokobong, you have joined now. Ayodele, Amid, you joined late. You overslept.
I'm sorry, sir. No, sir. I didn't set alarm for the class. Sorry.
Well, that's what you overslept. Amid,
Good morning, sir.
you underslept. That's underfitting, isn't it?
No, sir. No, sir. I've joined. I joined around 8:05.
Okay, but that's still late. Who else have I not called? Okay, so let's. Is it clear up to this point?
Yes, sir.
Great. So too many predictors can lead to overfitting. Another is when your sample size is very small. That can also lead to overfitting. So it's always good to have sufficient data points because you are splitting your data. So it's always good to have enough data points, even though no particular threshold for now. And finally, the third causes, or the third major cause of overfitting is lack of regularization. Regularization is a technique that allows you to prevent coefficient from fitting so perfectly, you know. So, you know, when, for instance, your R square is 99 point, it's not something to rejoice about. That could be evidence of overfitting. Is capturing it could be overfitting, which means yes, it's doing well within the data that you, but when you now use the same model in a new data set, you will be surprised it's not able to predict very well. So the implications of overfitting, here I have three options or three implications. One, poor generalization. When your model overfits, that may lead to poor predictive performance in new. We've said that. Whether new data, whether the unseen data, you know. So prediction will be poor. And model cannot be, the model cannot generalize the pattern in the structure or the inherent behavior of the data set. Two, the second implication is that it can be misleading. So you can have misleading model evaluation. So you can be overly optimistic, you know, in your estimates, and that can mislead you or researcher or analyst about the usefulness or effectiveness of the model. The third implication is the inefficient use of resources. So overfit models, they are often unnecessarily complex. So which means you will be using more resources than necessary. That's what, and that's inefficient. You are using more information when you just need very little. So that's inefficient use of resources, and that can lead to increased computational cost by having too many variables in your model, estimating too many parameters. That slow down the computational process and then increase the computational cost. In fact, it will increase the processing time, and not just the cost, but also time. And yet there will be no improvement in the model performance. So when we talk about inefficient use of resources, we look at the computational cost, the time, the computational time. Those two determines efficiency or inefficiency of a model. So complex models will require more computational time and increase the computational cost. So how do we detect and measure overfitting? Yes, we split the data such that we have data for training, data for test. So we will use the model in the training and then evaluate it in the test to see the performance. I've always used driving as an illustration. So training a data set is like you learning driving on a particular route. You are familiar with UI. So if you learn your driving from UI main gate to the central admin area of bookshop, that's where you learn your driving. So you'll be very good after some time that you can even close your eyes, drive from the main gate to the bookshop. That's training. So that model will do very well in the training data. But that, for us to know that you are really a good driver, so we will now need to take you to a new route completely. Route that was not used during your training. Maybe a route with heavy traffic, Mokola roundabout, for instance, take you to Ojuelegba, Lagos, take you to where else do you know? And then if you now drive very well, that's your new data, that's the new data set. And that will now determine how good you are. So to detect and measure overfitting, you have to split the data into two, the training and the test. And then evaluate the model performance in the test set. Then you can apply the cross-validation techniques. We've talked about the K-food cross-validation, which is very popular. You have the two-food cross-validation, so you can you there are several types of cross-validation techniques. You could Google for them. For instance, just Google cross-validation techniques in machine learning. So you could have quite a number of them. Yeah. So you can have K-food. Yeah. I want where they are all listed. Yeah, so these are major holdout cross-validation, stratified K-food cross-validation, leave P out cross-validation, leave one out cross-validation, Monte Carlo shuffle split, time series rolling cross-validation. Try to look at this. Let me add it to our classroom. Great. So these are three techniques for detecting and measuring overfitting. How do we prevent overfitting? Yes, you have to simplify the model, reduce the number of predictors, increase the training data, add more data point to the training data, use regularization technique, which is what we want. That's why we are even here. So one reason why we are learning penalized regression is because we want to be able to prevent model overfitting. Then you can prune. We will discuss this technique much later. So using decision tree approach, and then we will also learn about early stopping. So we can easily do this, no problem. We can easily do this, no problem. But today we will learn about this using regularization techniques. That's the end of the first part of our discussion. Any question? Any question? Dr. Olowokere is not joining.
The first part is clear to us, sir. No,
Okay, tell
no
me
question
one
for
thing.
now.
Tell me
About
one
one
thing.
thing is that is it that it sir,
Go on.
is it that it is only overfitting that can affect our model? Can't underfitting affect our model too in this aspect too?
Why do you
Because we
think
only talked
we
about
emphasize? Why do
overfitting.
you think we emphasize more on over? Can you define what I said about overfitting?
Overfitting is when the model we found we is able to capture the noise and as well the signal. That's overfitting.
No, no.
That our model is able to capture both the noise and the signal so that it can represent the training
No,
data very well.
no,
While
no,
in
no,
in the
no,
aspect of
no. Can somebody correct him? If you are using the concept of noise and signal. It captures more noise. Yes, than signal. It captures more noise than signal. And
okay,
therefore, it is able to do well in the training data set, but poorly in the test, in the new data set. That's overfitting. The reverse is the case for underfitting. So what will be the situation in underfitting? Can somebody tell me?
so it capture more of the signal than the
In,
noise.
in terms of performance.
In terms of it's okay, it is able to represent it perform well in the testing while perform poorly in the training.
Exactly. So that's why we are not bothering about underfitting.
Okay, sir.
Is that clear?
It's clear, sir.
So our concern is actually overfitting because we lost somebody. Okay. Our concern, well, your internet is deny you this converse. Mbokobon, you are not speaking. Is it that you are sleeping?
I'm here, sir. I'm listening.
Where are you listening from?
My house. I'm following.
Okay, what's your contribution?
My only question is, sorry, I'll be drawing us back a little bit.
Don't
Is
draw us
how
back. Don't draw us back. You watch the video.
okay. It's just about the underfitting, how underfitting works well in testing
when
data set
you
and not.
joined late. You joined late. I've explained that, and I have also just explained it.
Okay, sir.
Yes. Ayodele. Ayodele. What's your contribution now? I can't hear you. Abioye.
Yeah.
Yes, sir. Okay. I think Mr. Odile want to say something.
I don't think the network
Sir,
is
can you hear me,
helping
sir?
him. Better.
Yeah, I think that based on what my mate said earlier, that when it comes the reason, and you also mentioned that the reason why we are concerned about overfitting is because it performs well with the training data, but when we bring in a new data set that is not familiar with, cannot capture, the patterns that ought to be captured. So
Yeah.
definitely we need to be able to correct that, because the essence of fitting a model is so that it can, for predictive purposes, it can do well with data that is not familiar with. So we have to be able to correct the issue of overfitting. But in the case of underfitting, from the training data set or itself, it has not been doing well. So that has to be corrected. So we are not bothered with underfitting. Thank you, sir.
So how do we, what are the ways to get rid of uh, to simplify our model? Badmus. Or if Aboye is hearing me. How do we reduce the model complexity?
Yes, I can hear you, sir. Abioye, sir.
So how do we reduce our model complexity, or how do we simplify our model?
Yes, we can actually reduce our number of predictors. That's our number of independent variables in the model. So this will help us to simplify the model. So we won't have much predictors in the model to test around. So it will help us to prevent the issue of overfitting, and we'll have a better model for prediction. So that's one
Excellent.
of the
In the best offset regression, what techniques did we use to eliminate variables to select best subset? It's
we
also part of simplifying. It's a way of also simplifying the model complexity. What was the approach?
I think we use the adjusted R square.
That's not what I want.
We use all possible regression,
Uh-huh.
then forward selection and backward elimination.
Oh yeah, yeah.
We were actually using significant, the level of the significance level of the variables. So variables that are significant, they are left in the model. So we were using the statistical criteria, R square, just a p-value and all of that, isn't it? So, but in the penalized regression, we are not going to use those criteria any longer. So let's continue. I think I'm Essay. I've not heard you talking. Essay Blessing, are you there? Essay,
I'm here, sir. Good morning, sir.
good morning. It takes time to respond. Why?
Sorry, sir. So I just actually joined the class.
You slept off?
Yes, sir. So I'm on drugs, so I woke up very late.
Don't be on drug.
Yes, sir.
Sorry.
Thank you, sir.
So let's start with the basics of penalized regression. I won't repeat what we have talked about. Already I said penalized regression is used to reduce overfitting, is used to improve model generalizability, is used to select features. So that's clear. But let's look at the types of penalized regression that we have. The first one is the LASSO. LASSO simply means least absolute shrinkage and selector operator. Least absolute shrinkage and selector operator. So LASSO regression, if you recall, just block this one. The OLS that you used to know simply minimizes the sum of squares of the residual. Something like this. So if you are familiar with OLS, so which minimizes, the criteria is to minimize, uh, uh, maybe Z, or if you call it the sum of square of which is this sum of square of the residual So maybe I from 1 to n. And of course, this one is the sum of yi minus y cap square. So this is the sum of square of the residual. So this is the, which you can also call minimize the RSS. So this is what we know as the OLS criterion on minimizing. So in the penalized regression, you are also minimizing. But this time, you are minimizing two things simultaneously. You are minimizing the RSS plus another component. So, which means if this component is equals to 0, then the penalized regression reduces to OLS. So that's the point I want to make here. So we are minimizing the residual sum of square plus this other component. And that component is what I want you to look at very carefully. So we are actually minimizing there is a parameter here called lambda. And for LASSO, we are minimizing the absolute value of the individual coefficients, the square of the absolute value of the individual coefficient. Of course, there are k parameters there, so I will go from 1 to k. So, okay, I know there is no square there. In this case, there is no square. So we are only minimizing the sum of the absolute values of the coefficients. So these absolute values, they are coming from the OLS estimates. So, but this lambda is actually what we call the penalty term. This lambda is what we call the penalty term. And we also call it the shrinkage parameter, or the tuning parameter. And so if this value is equals to 0, you will notice that the entire thing here will become 0. Because what you see in that bracket, you can also expand it to something like this: lambda absolute value of beta 1 plus absolute value of beta 2 plus absolute value of beta 3 plus ... plus absolute value of beta k. And then you have this. So if this lambda is equals to 0, then everything in this bracket, which is the sum, will be equals to 0. It means there's no penalty. That's what it means. When lambda is equals to 0, it means there is no penalty. So if there must be penalty, there must be a value that is greater than 0. Therefore, lambda must be a value that is positive greater than 0 before you can talk of penalty. So, and the more the value of lambda, then the more severe the penalty that you are imposing on the coefficients, on the sum of the absolute value of the coefficient. So usually you take very large value of lambda, but the question will be, what will be the optimal lambda? Because if you continue to increase lambda, you might have a situation where, you are even causing more damage, more problem. So one will have to search for the optimal lambda, but that's another issue. But at the moment, what you need to know is that this lambda is the penalty, and the bigger it is, then the more severe the penalty, or the more you shrink the value of the coefficients, and they become very close to 0. The value of the coefficient will become very close to 0. So if the coefficients are not important, if the variables are not very important, the coefficient will be very, very small, or almost 0, so to say. So it's used extensively where feature reduction, where you want to reduce number of features, or where you want you have high dimensional data set, and you want to be able to improve model interpretability and performance. So that's LASSO. For ridge regression, the only difference is that instead of absolute value here, you are actually minimizing the component here is actually lambda sum of the squares of the coefficients, sum of squares. So instead of absolute here, you just have the square in the ridge regression. So ridge regression penalizes the square of the magnitude of coefficients. Unlike LASSO, all coefficients are shrunk by the same factor. No. So none of them will be zero out. So this method is good when we are dealing with multicollinear data, data with multicollinearity, or when the number of predictors exceeds the number of observations. There are situations where you have more features than number of observations. If that happens, you can use the ridge regression. Yes. Somebody raising up. Ayodele, yes.
Okay, all right. Thank you very much, sir. So I want to ask if you could speak more to that statement that when we have more features compared to number of observation, does it
Yeah.
mean that we can't use this kind of method in when we have big data? where the number of observations are very large.
Repeat yourself. Let me get
I meant, is it from what you just said that
yeah,
for ridge regression,
yeah.
that it can only be used when we have features that are more, or am I the one in that are more than the number of observation? I'm saying that in the case where we have big data, that the observation are going into maybe tens of thousands, and can it be applied?
Okay, look at this. Here you have 1, 2, 3. So let's say you have up to n. And here you have up to k. So n represents number of observations. K represents number of variables. Now look at this situation. Suppose you have 100 variables, observations, and you have 10 variables. You will notice here that n is greater than k. Now, in this situation, you can apply OLS. You can apply any other technique because you have more observations than this. But let's look at case where n is 10 and you have k to be 100. This situation, you have n less than k. OLS is not applicable. You won't be able to apply OLS. You won't be able to find the coefficients. But in this situation, ridge regression can be applied. That's what we are saying. Is it clear, Ayodele?
Okay, yes, sir. Yes, sir. Thank you, sir.
Great.
But sir, what I want to get clearly is that in the case where n is greater than k, can we attempt to use ridge regression too?
Of course, I said OLS and any other method will work.
Oh,
Whether ridge, whether lasso, whether elastic net, whichever, it will work.
okay, sir. Thanks,
Yes.
sir.
Any other question? Just
Ayodele.
Yes, sir. I can hear you,
So,
sir.
so just to repeat what Prof said, there would be no need for you to use penalized regression if OLS can perform the task. So when your N is more than K, you can use OLS and this other penalized regression, but there will be no need. It will amount to complicating, using a complex solution to solve a simple problem. I don't know whether you were in class when we were talking about overfitting and all of that. Were you in class then?
Yes, I was, sir. Yes.
Yeah, so these penalized regressions become relevant when OLS fails. Prof is back.
thank
Okay,
you.
thank you very much.
Thank you very much. I hope that is clear, Ayodele.
Yes, sir. Very clear, sir. Thank you, sir.
Okay, so you should be able to know the difference between the criteria the difference in the criteria or criterion rather of LASSO and REACH. So the criterion for REACH is to minimize the sum of the RSS and this term, no, this component. So then the elastic net actually combines this and this together. So you still minimize the residual sum of square as well as the sum of the coefficient of as well as this component of the LASSO and this component of the REACH regression. So so even though we introduce another parameter here, which is alpha, so this parameter, sorry.
Okay, guys, do you have any questions so far? We've talked about overfitting, underfitting, and the different types of cross-validation methods. Now we are looking at how to resolve the weakness of OLS. Any questions? The other thing that we can do while Prof is busy is to discuss two things. One, how to have time for our interactive sessions and practical classes, and also when is your exam, so that we can know how to pace ourselves. Yes, let's just respond to anyone before Prof joins. Ayodele, go first. Pick whatever you want to say. And if you don't have anything in relation to what I've said, feel free. Go on, Ayodele.
All right, thank you very much. I just want to get this clear that if I have a data set, that means my first approach to look at is for OLS. Then if I see that the assumptions of OLS are not met, then I'll ask that, okay, can REACH work here? LASSO, is that what it is, sir?
Yeah, so it's not that straightforward because your data set needs to go through more thorough investigation beyond just saying OLS. Remember that we are talking regression now. So your data will do prediction when it is numeric. So maybe I adjust your answer and say, if I have a data set that is numeric and I want to make predictions and it's a simple model, why would you want to use complicated models to solve a simple problem? So you are right, provided your data is numeric in the form that you can use the regression paradigm. Okay, but it is difficult when data becomes big. Remember that we said clearly that when the number of features is more than the number of observations, OLS will fail. However, there are situations whereby OLS might not fail, but won't be the optimal solution. I don't know if you got that point. It might not fail in the sense
Yes,
of you have few features and you have enough. So the complexity of your model will sometimes require complex models. So yes, you are right. If it's a simplified model and it's numeric, why not start with OLS? But there's nothing that stops you from using OLS and then using this ones and comparing. There's always, the issue of, cross-validation. The term cross-validation means you have used several models and you're trying to validate which one is most efficient. Did I answer you well?
yeah, thank you very much, sir. Yes,
All
sir.
right. Yes. Any other person with any other thing from what we have done, or maybe issues that have to do with pacing ourselves so that we can cover enough ground before the exams, or things that have to do with practical implementations, because we don't have sufficient time to stay in class and also do practical implementation. Yes, Abioye, go on.
Thank you so much, Mr. Peter. So my observation is just on based on the last practical prof gave us, and some of us, at least I know that we have attempted it, but from my hand, my major issue is how to interpret those things. And sometimes when we are trying to sort out this code, we fall into some error that is kind of difficult for us to really understand uh, why that error is coming up and what's the solution to that error. So I don't know if there are still some things we still need to know so as to guide us through, number one, correcting these errors, how to identify them and to easily correct them, and number two, how to interpret our output. Thank you, sir.
Okay, thank you, Abioye. So that's one of the things that we try to, accomplish in our form of learning in this particular course. That is about collaborative learning, okay? So when you are given these exercises, you are not expected to just run through it once and then you get the results. It doesn't work like that. You will come across errors, and through troubleshooting, networking, searching for solutions, which you guys don't do, you get better on the job. Don't worry, let Prof continue the class. We'll return to that later. Prof, welcome back, sir.
Thank you. Sorry for that. Oh, sorry. Oh, God.
So let's not put Prof under pressure. Let's just allow him take his time. We'll talk about those issues later. Okay, class?
All right, sir. All right,
All
sir.
right, okay, cool. So he has stood up. However, let me tell you first, the version of R that you are using and the version of R Studio that you are using matters a lot when you are implementing, all of this. Secondly, nobody gets better doing coding without trying to, resolve the error first personally. Also, you become better when you have tried and you now seek for help. The danger in coding is when you just, copy and paste and it runs, you don't learn the implementation of the code. And then if you have problems with interpreting those results, one thing that I've discovered that I'm also guilty of is that we don't even go to the particular library and read how the library is used. Also, when you want to use a function and you put your cursor in front of that function, it tells you how to fit in those things. But we are so much in a hurry, we want our code to run. Okay, let's pause again. Prof.
Hello.
Go on, sir.
Okay, thank you. Sorry. I might be having this because of too many things.
Yeah. That's why you are the prof. That's why you are prof, sir.
She's calling again.
Yeah.
Hello.
You can receive the call, sir.
Huh?
LA mute can receive call. Okay. So what am I saying? Or what are we saying? We are saying that you need to read the documentation of those libraries. Don't just check the code that Prof has given you. Oh, GLMET, run, good, install, library, then you have error. I run to Google and then come back. No. On your own, apart from submitting an assignment and doing that collaboratively when you have opportunity, you must also understand the library. That's what makes a difference. We'll continue that conversation. But I saw Joseph raise his hand before. Joseph.
Good morning, sir, Mr. Peter.
Yeah.
Okay, you raised the issue of we meeting to discuss, and
Yes.
that's what I want us to talk about now. When are we starting? How soon are we starting?
Okay, so let's do it like this. When are you having exams?
It's not yet announced.
Okay, so we need first to cover enough of the curriculum. Okay, it's possible that by the time your exams will be announced, we will not have covered the curriculum. So it's also possible that Prof might ask us to handle some of those lectures together. When we have those opportunities, we can use them as physical classes, okay? But what I was talking about was how you can upskill, apart from the content and the tutorials, and how you can ask questions and then ensure that you are well prepared for the exams. There's something about statistical data mining that I want us to enjoy together. The fact that we can use this to learn how to do computer programming up to the level where when we are left alone, we can go outside and say, I've started data mining, I know a bit about machine learning. For me, I prefer to use Python. That's me, okay? But for the purpose of, going through your assignments, I will suggest I will use R to do the exercises. I'm sure that we've mastered our R better since that's what we used in the previous semester. But I desire to use Python. So those are conversations that are left to you. If you say, let's stick to R, beautiful. When we come to class and we do our practical demonstration, we use R to learn, penalized regression, best subset regression, and those other concepts that will come after. In terms of fixing a date, I leave that to you to discuss even right now as we wait for Prof. And then let's come to a conclusion so that when I come to UI, I think I should be in UI like 2 or 3 times next week and perhaps the week after. There's a task that I'm running on behalf of Prof. That would put me in that neighborhood. That sounds cool. But I wanted to know when your exams will be coming up so that if we go for such short classes, we won't be doing programming. We'll rather be covering the curriculum so that you have good space. Permit me to also ask, have you registered for tomorrow's program? There's a program tomorrow at the International Conference Center. Let me tell you, you might find it interesting. I'm going to bring there about 30 pupils, students, because I know what that conference is going to do to anybody who wants to make progress in this field of data science. You cannot stay in your living room and be proficient at data science. You become proficient by attending conferences, listening to people who have gone ahead, in addition to really hands-on. Yeah, I'm saying several things deliberately so that others can speak to any part of what I've mentioned. So the floor is open again.
Sorry, I'm back. Let's quickly make progress, but I might see that interruption.
Hold on. Prof is back.
So we'll talk. Now, I've talked about 3 different penalized regression, the LASSO, the REACH, and then, of course, the elastic net. Elastic net combines the features of LASSO. So it's an hybrid. So it combines the features of LASSO and REACH regression. So the LASSO penalty is called the L1 penalty, and then that of the REACH is called the L2 penalty. So the 2 properties are combined in the elastic net. So this elastic net is useful where there are correlations among the predictors, where you have multicollinearity. Amit was responding on something related to this during our seminar yesterday. So you can use where you have correlation among your predictors, you can conveniently use this technique. So it will address that in your regression model. So and in fact, when predictors are correlated, elastic net can outperform LASSO and REACH. That's very important. So most people are still bothered about ordinary least square the linear regression techniques, which actually the underlying assumption is that there must be no collinearity. But if there are, you can use elastic net regression instead of using ordinary least square regression. So now let's talk about those key elements. So, and I've mentioned them before. Sorry, I have to pick the call again. Sorry.
Yeah, Abioye. Abioye Oluwafemi.
Yes, sir.
Go
Thank
on.
you, sir. Yeah.
Go on.
So what I'm about to say the other time is it's still based on our meeting in terms of tutorial and all that. So please, I want to solicit that we should not actually wait till when we are close to exam before we have those tutorials. I just want to say that once we cover like maybe a significant level of the lecture, we can start so that we are good at these things. Once we are expert, even going to the exam, I mean, when the time of exam actually approach, we might not really have to bother you as such. What we just have to maybe tell you is little places, key points that we are overlooking or oversighting. So that's just my
Yeah.
addition to.
It makes sense. Badmos.
Yeah, thank you, sir. Thank you very much, sir, for your time and everything. In addition to Mr. Abioye comment, I don't say you have said it all. The major purpose of learning these things even supersedes writing exam. Writing exam is just want to write as an academic requirement. But what we need, according to your point, you always tell us is to skill ourselves. We appreciate it if we don't wait till that exam period. In fact, if you are able to even to get it well, more than using the writing exam, if we understand it well ourselves and we knows it well, even we can write exam. Writing exam is not even a problem. So that's just addition that I have with Mr. Abiy. I
It
will
makes sense.
appreciate if we can start on time, sir.
It makes sense. What you
Good,
said.
good morning, sir.
Go on.
Yes, sir. To add to what they have said already, with the timing, we can work with your time. We don't necessarily have to fix a time for you. So since you say you'll be in school next week 2 times, we can just fix the time for it along within the time frame you'll be in school. I think
That
that will
makes
work.
that makes sense.
Then
That
also
makes,
for the programming language, I'd say Python, because we're already using R for like 3 courses that we are doing this semester. So I think that's enough. We can, if we are doing something that we would need for the future, we should just use what's best, which is Python. That's my
yeah,
personal opinion.
that also makes sense.
Then
Joseph.
for tomorrow's this thing I've registered.
Oh, that also you've made a lot of sense today, all of you. Joseph.
Yes, sir. Thank you, sir. I just want to do. They've said many of the things I want to say. One is that exam is not in view yet, and again, I'm thinking if we can maximize the time or use the opportunity when you be coming around next week to interact, sir, and also so that we can match this our theoretical understanding with the
It makes sense.
practical.
It makes sense too. Amit.
Good morning, sir. Thank you so much, sir. I'm also in
Yes.
support of what they have said that even if possible to, you can as well have a time, maybe when you don't have time to come physically, you can as well have a virtual class. If possible, you can have that with us too, so that you keep on learning every time, because this require for us to understand it better. We need to be doing it continuously and consistently with it. So I believe
Okay. So
that will help.
let me just quickly try to respond. How is your timetable like this week? Let's listen to it. When are the times that you reckon
Uh,
that it's a free period?
Basically, Monday and Tuesday is our class. Is when we have like the main class. The rest of the week, we don't usually have much class unless
Okay,
on
so
Friday. Then
Wednesday is public holiday.
2 to 4.
Yeah, so Wednesday is public holiday. That's May 1, Workers' Day. So if we can have class on Thursdays, can you check your timetable?
We are free on Thursday.
Yeah, so it's possible that when I come, maybe around, let's say something like 1 to 3, we can have 2 hours. Okay.
But is it possible? Can't we meet on Wednesday too?
There's public holiday, Workers' Day. Workers should rest.
Okay.
All work and no rest.
It's not good.
Somehow.
Workers should rest.
But did not be firewood. Don't worry now. So in preparation for that class, let me ask, how many of you have installed Python on your system before? If you have not, okay, Abe, go on.
I've not, but I will.
No, I'm actually indicating that I have. I'm actually indicating.
So when you want to install Python,
but I'll try to.
Yeah, try to install anything from Python 3.10. Python has come in 2 flavors.
3.10.
Yeah, maybe 3.9. We'll find out. Maybe 3. I don't know. Maybe 3.710 or something like that. I don't remember. Okay. So, but the point I'm making is this: don't install Python 2.10. Joseph, you want to say something?
Yes, sir. I once installed Anaconda on my laptop, but at the point it was not responding again, so I uninstalled it, and now I'm having issues with my Python. So even though I've been trying to use Google Collabo, but that was I have to connect to the internet.
Okay, so we have talked about so many things in this class, one of which is to be ready for employment, whether as a researcher, lecturer, in academia, in industry, and all of that. So when it comes to data science at our age, let me become your age, you need to develop a repository. That is, you need to have your own portfolio. And where your portfolio resides is in the cloud. So if I were to advise you, I would say, why not use cloud platforms? And that's why I'm asking you to download Python 3. If you download Anaconda distribution, there are 2 types. There is the offline version and the cloud-based platform. Any tool that you want to use going forward should be cloud-based. You need to spend resources. You cannot improve your skill if you don't spend. But how much do you spend? You know how much we spend on social media, WhatsApp, eating puff and drinking Coca-Cola. They are good, they provide energy. But Prof is back. Let's allow Prof. We'll talk about this conversation later. Prof, welcome back, sir.
Thank you very much. And please, I'm very, very sorry. Part of why I'm having disruption is tomorrow's planning for tomorrow's program. So the organizers are just calling me to iron out 1 or 2 things. I hope some of you will also attend. Now let's continue. I've mentioned earlier that the parameter lambda is called the regularization parameter. That lambda you see plays a very key role to determine the impact of the penalty on the regression equation. And I've told you, when you increase lambda, then the more is the impact of the penalty on the coefficient. So, and when the lambda increases very big, when lambda is big, then coefficient will be shrink. When we say coefficient shrink, it will mean the coefficient will be reducing and possibly approaching 0. So the trade-off between bias and variance in penalized regression techniques, you are actually, those penalty you are doing, you are actually involved in a trade-off. You are trying to somehow do a trade-off here between bias square and variance. So by increasing, as I've explained earlier, by increasing, maybe you started with a very complex model. So as you are reducing, you are reducing the variance, and of course you are increasing the variance and you are reducing the bias. So that's what is happening. That's what we call trade-off, until you now have a sort of balance. You strike a balance and you get your optimal value. So penalized regression involve, is anybody asking the question? Peter, yes. Okay.
Prof, just a moment, sir. I want to tell them something.
Okay.
So I applied for a data science fellowship program, and one of the questions they asked me was what Prof just said. They wanted me to explain bias variance trade-off and the issue of L1, L2 regularization. So don't take these things for granted. I was accepted, I did it, and it has added to my portfolio. So it's important. Sorry to interrupt you, sir.
Thank you for so these little things they can't. So please, that's why I try as much as possible to give you the details, to make the note a bit lengthy, instead of just having the mathematics. So what are the practical considerations? One, when you are to choose your lambda, because I told you, if you choose lambda that is 0, then you are back to the linear, to the OLS, to the ordinary. So any value greater than 0 is what you need. And there is no maximum, 1 million, 1 trillion. But there is an optimal lambda. Unfortunately, there will be a point when, if you continue to increase lambda, you are no longer going to get optimal model. You will now be getting model that is also suboptimal. So what is that number? Which is that is the big question you have to one has to be able to answer. So to be able to get the optimal, you now use the cross validation to be able to determine the optimal lambda. So cross validation technique, you can see, is very critical as far as in solving model complexities. So in choosing your lambda, you rely on cross validation method technique. Then standardization. If you are applying penalized regression, you must standardize the predictors, the dependent variables or the feature, so that they will all be on the same scale. So what do you mean by standardizing variable? So which means, does anybody know? Does anybody know what it means to standardize a variable?
Yes.
So if I'm to standardize x1, it means I will find the mean, the x bar 1, the mean, and then I will now apply z, which is xi, x1i minus x bar 1 divided by the standard deviation. the standard deviation for one, because this one will also have its own standard deviation. So this is the formula for standardizing the variable. You will also standardize this, you standardize this, so that if this is age, which is measured in years, if this is weight, which is measured in kg, and whatever, by the time you now standardize, all of them will have the same unit of measurement. So standardizing the predictors so that they will be on the same scale. So this will prevent the model from unfairly penalizing variables simply because of their scale. Then another practical consideration is the software. Our package is what I've always been recommending, but there are other packages, other software, including Python, that you can use. So in R, you can use the GLMNet package for LASSO, for Reach, and then even for Elastic Net. So you can also use it to select the optimal lambda using through the cross-validation technique. Now, that is the end of that section. How do we choose between LASSO, Reach, and so on? These are the key things you need to take into consideration. One, what penalty type are you interested in? So LASSO penalizes the absolute values. Reach penalizes the square, which is the L2 penalty. LASSO is the L1 penalty. But this can lead to some coefficient being shrunk to 0. So some coefficient will be 0 completely. But in the Reach regression, they won't be 0, but they will be very close to 0. So all the features will still be in Reach, whereas some features will be eliminated, will be removed completely in the LASSO. So LASSO does not tolerate any irrelevant, useless features. That's why even if the variables are correlated, you can still use the LASSO regression. So the other thing is, when you have to choose, is the impact of the model coefficients. So LASSO tends to produce simpler and more interpretable models, where the less important feature coefficients are 0. So Reach, on the other hand, will give small but non-zero. The coefficient will be 0, will be very small, but it will be non-zero across all the features. And that can still be very useful when you want to at least draw inference from all the features. But LASSO will remove any, will remove anyone that is not useful. So, and you won't be able to interpret it. So you won't be able to measure the impact, rather. So those are two major key differences in the LASSO and Reach regression. Factors to consider when choosing LASSO and Reach. One, if you want to do feature selection. So one, if the goal is to reduce your models if your goal is feature reduction, to be able to simplify and be able to interpret, choose LASSO. So if you have high number of features and suspected that many of them might be relevant or redundant, so you can choose LASSO. LASSO will remove the redundant variable. If you have issues with the multicollinearity, your preference could be the ridge regression. So it will deal with the multicollinearity, and as well you'll still be able to measure the impact of your variable, because the variables will still be there, only that the coefficient will have been shrunk. When you have number of predictors, well, another factor could be number of predictors relative to sample size, which I've talked about. If you have more predictors than your sample size, then you can use, you may want to use a LASSO regression. That one usually happens if you are dealing with households, firms, and you have there are situations when you have more features. If you collect, there are situations when you do survey, you have long list of potential features than the number of samples that you have taken. So you can consider the use of LASSO. If you also want to make your interpretation simplified, LASSO is also a good one. In terms of prediction accuracy, then ridge regression might be your best bet. So these are factors that you can use to consider the choice of among LASSO and ridge. So what are the ways to implement this? You can use cross-validation. I've said that many times. You can also use the hybrid approach. If you are not satisfied with LASSO, not satisfied with ridge, the elastic is the midwife. So you can opt for the hybrid approach. The hybrid approach is the elastic net. Most people like LASSO, but for the simple reason that it will shrink to zero and then give you a more compact, more simplified model. So the last aspect of our lecture is the practical applications of penalized regression. You can apply it in finance, in the area of credit scoring, where you want to predict credit worthiness of individuals based on their financial history. For instance, in the bank, for those customers who apply for loan, before you give them loan, you can now have credit scoring, which credit scoring will show whether the customer is credit worthy or not, and that will mean that the financial history will be used as the predictor. Maybe saving history, withdrawal history, then credit application history, and so on like that. So it can be applied in finance for predicting credit worthiness of a customer. It can also be applied in portfolio optimization, where you want to minimize risk by diversifying your investments. So you'll be able to determine the best subset of assets that you should consider to be able to minimize your risk. In the healthcare sector, you can use it for disease prediction, to predict whether patient outcomes is based on clinical and demographic factors. So you can choose the best subset or the best features, clinical features, demographic features that will help to predict patient outcome, maybe for COVID or any disease for that matter. It can also be used in genomic data analysis, where you study genes. In fact, the development of penalized regression is traced to genomic data analysis. In marketing, you can apply it to customer retention and campaign optimization. In customer retention, you want to predict customer churning based on their interaction and transaction data. Let's say in communication, whether customer will move from one network to another network. Campaign optimization, to also determine the key factors that lead to success of market campaigns. You can apply it in real estate to predict price. You can apply it also in technology, in ICT, to detect spam, maybe to classify emails into spam or not spam. You can use it also in text analysis, maybe in sentiment analysis, to be able to determine social media pattern, whether it's social media sentiment, whether positive, negative, or neutral. So these are different application areas. And if you want to do applied work, maybe for your project, these are areas you may want to consider to do your project on. Finally, for software implementation of penalized regression, these are some snippets, R snippets for you to work with. So here I've given you the snippet that you can run with the data that I gave you. That's the data on car owners. You have the data on car owners. So were you able to run how many of you were able to run the one I gave you for best subsets? Were you able to run yes? Nobody is responding.
Yes, sir. I have to run, sir.
Did you run it individually or you run it together?
Individual, I think.
Is nobody came to me to complain
Individual.
or to ask for assistance? I'm still expecting your your report on that. So for this one also, try to run this, follow the step-by-step procedure here. You can see we don't have time to do this. Though in LISA, I'm planning that we are going to have a one-day special training on penalized regression. Maybe sometimes in May or June. It will be just for practical work only. So we will be able to apply it to solve different problems. Some of them will come from finance, healthcare, marketing, real estate, and so on. So you might look forward to that. So this is the end of this lecture. You have the hands-on exercise. So prepare the data that I've given to you, the data on demo. The data is on our Google. So you are going to use car price as your dependent variable, age, income, education, gender, car category, retire. All of these ones will be your features. So you will now follow this step to be able to run the LASSO regression. Follow this step to be able to run the ridge regression. Follow this step. Yes, answer whatever questions you have here to be able to compare and interpret your results. So I want your solution to these exercises. And finally, we have this multiple choice. Some of you have done it very well. So let's go and quickly look at your, nobody can submit again. So I'm no longer accepting responses for penalized regression, pre-lecture quiz on penalized regression. So the list I think is 13. 2 score 14, 1 score 16, and 1 score 17. Let's look at some of the questions. So, all of you seem to got this. What is the primary purpose of adding penalty term to a regression model in penalized regression? So the correct answer is to prevent overfitting and improve model generalization. Which type of penalized regression is known for shrinking coefficient to 0? So we've discussed that is LASSO. All of you seem to got that one. What does the alpha parameter in the elastic net regression, what does it stand for? So it's actually the ratio of L1 and L2 penalties. 3 of you got 2 miss. So it is not the magnitude of the penalty term. The lambda actually is the magnitude of the penalty term. Which statement is true about ridge regression? So every other one is false except that it reduces the model complexity by imposing a penalty on the size of coefficients. We also got this. So in the context of LASSO and ridge, what does shrinkage mean? It's simply the reduction of regression coefficients towards 0. That's what shrinkage means. Why might you choose LASSO regression over ridge regression? Yeah, to potentially reduce the number of predictors because it will set some coefficients to 0. Which regression technique will be most appropriate when dealing with highly correlated predictors? Ridge regression is the answer. If you are dealing with highly correlated regressors or predictors. You can use ridge regression. So it will reduce the impact of those variables, completely. What is a common use of elastic net? Yeah, to balance the properties of lasso and ridge. Only one person missed this. Which penalty term is associated with ridge regression? L2. So L2 is the one that minimizes the RSS plus lambda sum of square of the squares of the coefficient. That is the L2 normalization. Elastic net is particularly useful where there are more predictors than observations. Yes. So what role does parameter lambda play in LASSO and ridge? It controls the trade-off between bias and variance. You all got that right. And then what is not a direct benefit of using penalized regression? The answer is that it automatically performs feature engineering. And finally, nobody got this correct, in which, sorry, not even finally yet. In which scenario might you prefer to use lasso regression for variable selection? The answer is this: when you are unsure about which predictors are important. So, ridge regression is less likely to obtain sparse solutions because it does not set coefficient to 0. Yes, so you all got that. That's one. How does elastic net create a balance in penalized regression? So by combining L1 and L2 penalty, you all got it. And again, which method will you use if you need a model that is easy to interpret due to its simplicity? Most of you choose LASSO, but ridge regression is the answer here. So cross-validation is important in penalized regression. I've said it earlier because that helps you to determine the optimal value of lambda, and which is typically minimized in the lasso regression model. So the sum of absolute coefficients in lasso. So in ridge, the sum of squares of the coefficients. Which statement about ridge regression is correct? It penalizes the sum of square coefficient. I just said it now. And why might a data scientist opt for elastic net over lasso or ridge? Well, to handle both particularity and feature selections effectively. That's, you all got that, and that's the last question. So, thank you all, except there is any question. We have come to the end of the class. Any question? Nobody in the class? Is it because SA is not feeling?
We're in the class, sir.
Okay. So this is the end of the lecture. Enjoy the rest of your weekend. Peter, thank you.
Thank you, Prof. Thank you very much, sir.
Honey seem to have gone. SA, take care of yourself.
Thank you, sir.
Okay, so bye.
Bye, sir.
Thank you, sir.